Chapter 2, we're going to focus on network architecture and components. After completing this chapter, you're expected to be able to identify network devices, identify network topologies, distinguish between network types, recognize components of visual local area networks, and identify functions of modern network devices. Network components. Before we look into the core network devices, let's begin with a definition or understanding of endpoints or host. In TCP/IP terms, these are edge devices that basically process, communicate, send, and receive data on the network. For instance, you've got computers, telephones, modems, or servers. Keep in mind that a host requires a network interface card to be able to access the network, and it must have an address in order to be found on the network. Also keep in mind that a modem is a type of a network interface card that connects a host to an analog circuit for connection to a network. A modem simply modulates and demodulates. Also keep in mind that computers and servers are hosts on the network. Therefore, a computer is called a client when it runs an applications for end users, whereas a server is a server because it runs additional software to provide services on the network in support of the clients. Also keep in mind that telephones can be connected to IP networks as hosts, and they do transmit a person's voice over the network, commonly called voice over IP. Take note. Now let's get to the core network devices. Computer networks employs various types of hardware for access, range, and security. The following core network devices that we're going to touch on are gateway, router, switch, bridge, repeater, WAP, and NIC. Keep in mind their similarities, their differences, and the level at which they operate at the OSI model. Gateways. Gateways are created with software that can run on PCs and routers. Gateways link different programs or protocols. It thus examines the entire packet, including the data portion, to translate incompatible protocols. An example of a gateway is the services that run on a router. Gateway services can link an IP network to an IPX network, so the users on the IP network can communicate transparently with the users on the IPX network and vice versa. Keep that in mind. Jumping onto routers. Routers are a step up from bridges. In chapter 1, we mentioned routers, we talked about routing. While bridges filter by MAC address, routers do filter by hardware and network address or IP addresses. While repeaters operate at layer 1, bridges and switches operate at layer 2, and routers operate at layer 3. Keep that in mind. Be aware of where routers operate. Routers do operate at layer 3. Another thing that routers do is they do open the data packet and reads the network address where the data packet is being sent. And this is done by determining the destination address. The router prevents unnecessary network traffic. Yep, they always check it out, be able to see which one is the best route. They will encapsulate and they will route it out. Repeaters. Get it? Repeaters just basically regenerate and propagate signals from one network segment to another. They do not change the address or data. They only pass the data on. That's what they do. Unlike routers that can filter, repeaters cannot filter packets. Even though repeater helps to extend network distance by regenerating weak signals. Hops. What is important about hops is you have to know what they do, which is they connect our computer local area network connection into one device or concentrator. And what happens here is PCs can be connected to a hub using coaxial or twisted pair cable or even radio frequencies. Hubs can be considered multi-port repeaters. They do concentrate all local network connection onto one device. That's it. Let's get to bridges. Like switches, bridges also regenerate signals, but they are more intelligent devices than repeaters. Keep in mind that a bridge can read the destination MAC address or the hardware address from the data frame and determine if the destination computer is on the local segment. Remember that bridges do operate at layer 2. Switches. Unlike hubs, switches can run in full duplex mode. And what does that mean? It means that computers and switches can both transmit and receive simultaneously. Are there any differences between switches and hubs? Absolutely. It is. When a computer transmits a digital signal to a hub, the digital signal is sent to all ports attached to that hub because it is physically connected using a wire. Whereas a switch sends it only to a specific port where the destination MAC address is located. Hubs they are not as intelligent as switches. Switches will use the MAC address and they'll kind of pick out what device. But with hub, because they are physically connected using a wire, it just blasts it through. Everyone on the connection gets it. Wireless access points. Be aware that they are similar to hubs in the way they handle data. Therefore, all devices that are on the wireless access point receive the data that is shared by the wireless access point, irrespective of the MAC addresses or whatever, irrespective if that data was destined for a particular device on that network. The only difference that the WAP has with hubs is It does use a wireless frequency to send and receive data, whereas hubs devices are connected using a coaxial twisted pair cable. So when you hear a twisted pair, it's an Ethernet cable. Network interface card. We talked about this already, right? A host must have a network interface card. They are devices that provide a physical network connection to systems, such as all the devices that we just looked at. And computers, laptops, servers, and all hosts connected to a network. Without a NIC or a network interface card, devices will not be able to operate at layer 3. It's very important. The only thing to kind of be focused on when it comes to hybrid network devices is just to kind of understand what a multi-layer switch, right? What is a router, right? We all know that a router is a combination of a bridge and a router. And this hybrid network devices become something of today's operation due to the complexity of today's network. For instance, we touched on modems. If you ask somebody, have you ever seen a modem? They'll tell you no. But a modem does exist. But it's actually embedded in a router. It modulates and demodulates and just blends with the router and be able to assist the router to be able to do that routing function while it does the modulate and demodulating piece in the same device. So keep in mind what is called a multi-layer switches. Multi-layer switches. They are routers. A device that has a combination of a bridge and a router. We've talked about routers, routing. You can read that. Switching. Cache-based switching. Cache-based switching in this case is in a situation where a router receives the package and realizes that the package is not complete. They will save that piece of the package, right? They'll cache it in what they call the fast lookup table and waiting for the other piece of the remaining package. Once they get it, they put it together and they send it out for delivery. We've also touched about Cisco Express forwarding. You might have read that in chapter 1 or in this chapter as well. The CV allows for fast forwarding of data at layer 2 and layer 3 by building new tables to hold the information in hardware. It's good for a better understanding of this course. The building the forwarding information base table, just read that. Better for your understanding of this course. Building the agency table, you want to just read that for your understanding of this course. However, it's always good to understand how things have been prepared for to transmit. Four major steps are involved in transmissions, right? The routing device changes the source MAC address from the sender's to its own, which is the router, right? You send a message, the router picks it up, changes your MAC address from the device that it's coming from, and then replaces it with its own. Secondly, the routing device changes as well the destination MAC address from its address to the address of the next hop. If it has to connect to another router, right, it's going to use that destination address of that router. Step 3. The time to leave is decremented by 1, which causes the IP header checksum to be recalculated. So the time to leave is kind of like, hey, if it's going to have to hit 3 routers before it gets to its destination, then that 3 routers is the time to leave. It means 3. So every time it moves from one router to the other, right, that decrements. It will reduce. So if it moves from the first router to the second router, then the time to live will be 2. Finally, the frame checksum is recalculated. It's just good for a better understanding of this course. I guess we'll conclude with the components. Let's get into network architecture here. When it comes to network architecture, there are 2 things you have to take very seriously here. So, in order for us to have a successful and reliable network with a high throughput, 2 things are very important. Those items are a collision and a broadcast domain. A collision and a broadcast domain. Collision domains are network segments with multiple hosts. Keep that in mind. Collision domains are network segments with multiple hosts. They are created using devices such as hops and WAPs. Additional collision domains can be created with bridge and switch interfaces. The second item that is very important for a successful network is broadcast domains, like I mentioned earlier. Broadcast domains are the area of the network in which all devices see and participate in transmitted broadcast sent from all other hosts and servers in that same area. Broadcast domains are created by a routing interface on a router. Multi-layer switch, we talked about that. Firewall interface, or some other device that has the ability to route. So the key takeaway here is, in order for us to have a successful and better operation network, we need to have a collision domain and a broadcast domain. And when we talk about broadcast collision domains, there are multiple segments that contain host. There are segments in the network that contain host. And those hosts, we talked about hops and wireless access points. And the second to that is a broadcast domain. And these are areas in which all devices see and participate in a transmitted broadcast sent from all other hosts and servers. And they are created by using router interfaces on the router, multi-layer switch, firewall interface, and some other device that has the ability to route. For a better understanding of a broadcast domain, just 3 things are necessary, right? And you can read them in a quite a way. For instance, a unicast is a message sent from a single computer that has a single destination host. And with broadcast domain, if a computer knows the address of the destination host, a message can be sent directly to the host. If the same computer does not know the address of the destination, or there is a message that the host wants all computers to receive, then a broadcast message can be sent. Third, a broadcast is a one-to-everyone communication. All computers in the broadcast domain receive the message. The following figures that you see from figure 2.1 right down to figure 2.4 just shows the relationship of collision domains and broadcast domains in various with the various device interfaces. In figure 2.1, the diagram shows a single hop with 4 hosts connected. A single hop with 4 hosts connected. Therefore here, the hop is the only collision domain, and it also serves as the broadcast domain. If it has to send the information to all the computers, it will be able to send it. If it has to receive and redirect, it's going to do it. It's just a single hop. So, the diagram on figure 2.2 just shows us the bridge used to create collision of interfaces. In this diagram, rather than using a hop, it is a bridge that serves as a collision domain. and also serves as the broadcast domain. The diagram on figure 2.3 shows a switch used to create independent collision domains. In this case, it's now a switch used to do that. And the diagram on figure 2.4 shows a router with interfaces that creates a new broadcast domain. And every new broadcast domain, there is a new collision domain within it. A single interface on a router can be called any of the following terms. Just keep that in mind. So if you have a question that asks you about what kind of single interface on the router be called, if you could either be called a network segment, a broadcast domain, or a subnet, because it serves those purposes. And just look at the diagram. This is a router. Each interface is a separate collision domain and broadcast domain. Yep. Okay, let's look at address learning and forwarding. With address learning and forwarding, those core network devices that we touched on, bridges, hubs, they're very important in this process and at the various layers that they do resides. We'll begin with what a switch can do as its primary function. It performs, all it does, or its primary function, is address learning. Address learning makes intelligent forwarding decisions possible. Without the ability to make forwarding decisions, the switch would be a hub. And we've looked at those differences and what those various core network devices do. So it's just kind of a reminder of what a switch does, what the responsibility of a bridge is, and their responsibilities linked to what address learning and forwarding is all about. We've read that already, so you can go into the details and kind of just read and understand on how to get a more detail on how they perform. Switches do exactly the same thing like bridges, but they can forward the frames much faster than a bridge. And reason being that there are processes in the hardware instead of in the software lookup that a bridge performs. That's why. What is very important with address learning and forwarding here is just the process and how it performs and what happens. For instance, here, when a switch first boots, any other connected host have sent any frames of traffic, the MAC address table is empty. Yep. The moment you boot a switch, the MAC address table is empty. When a host sends a frame, the frame is received by the switch. The switch looks up the destination MAC address for the receiving host, but it is not listed in the empty table because that table at the time it boots, right, it's empty. What the switch does now is the switch floats the frame. It floats the frame. It kind of broadcasts, right, out all of its interfaces. It broadcasts to all its interfaces except the frame of the sender, except the one in which it received the frame. In this case, Ethernet O, which is always the default, and interrupts every host on the segment. The sender host, which is A, which sent the frame, would now have its MAC address in the table. When the receiver host, which is host B, sends a frame back to respond, the switch enters the receiver's host, which is host B's MAC address, into the table. Host B, which is the receiver that sends a response to the frame out using the Ethernet or directly to host A, which was the initial sender, which does not interrupt the other host on the segment. So what happens here is when the switch boots, it has an empty table. Its MAC address table is empty. So as host starts interacting using the switch, that's how the switch grabs your address and log it into the MAC address table and get to know which location folks are. So it's pretty self-explanatory. If you've never sent a mail through a UPS, they won't know about your address. So the moment you send out one, they'll document and says, okay, we've got a client here that sends mail often, and this is the address, this is the location. So every time a mail comes in, they don't have to scramble and look for your address or somewhere making phone calls. They already have it on their table. That's just what figure 2.5 explains here. An empty MAC address table. The diagram of figure 2.6, it's a populated MAC address table. Here it was empty. Here it's populated. You can read this just to understand. It's self-explanatory. The table in figure 2.7 depicts two modules switching numbering. You can read this to get an understanding. Why a fast Ethernet is 0/1, and it's pretty self-explanatory. Read it, please. Read it for a better understanding of this course. Network topologies. For a better understanding of this course, it's important for you to know how links and nodes of a communication network are arranged. And this is what network topologies is all about. The characteristics of the various topology are important for you understanding why you have to choose one network topology over the other. The characteristics, it gives you the reason why you have to make those decisions. Let's begin with bus topology. With bus topology, all devices are connected to single cable. It's inexpensive, you can see here. It's on the cheaper end of the network plant cabling. Therefore, it's inexpensive. It's also known as a linear bus, where all devices, like I said, are connected to a single cable. Another name for it is called a trunk or backbone. Most often, this cable plant is either coaxial cable, called thicknet, and thinnet, depending on the generation and thickness of the cable. Coaxial cables are not expensive, so that's what makes it very inexpensive. Computers are connected to the bus using a drop cable, more often called a T-connector or a vampire clamp. Figure 2.9 shows you what a bus topology is. Very simple, very inexpensive. The next topology is called the star topology. In the star topology, as you can see, it has the shape of a star. Each device connects directly to a network device, such as a hub, a bridge, or a switch. So you see, you have to spend money to buy a hub, bridge, switch, whereas on the bus topology, it's just a coaxial cable to connect to, talk to each other. With star topology, each device has its own cable. Yep, you gotta spend money separately, right? Whatever it does, you do for one, you have to do for the other. With a bridge or a switch, each device interacts in its own collision domain. Yep. Cost is higher with network devices, and there is more cable involved. Troubleshooting is easier with separate connections to each device. Yep, troubleshooting is easier because if a computer fails in connection, you could easily narrow it down to that section of that computer and troubleshoot it. Additional network devices can be added to create a hierarchy style. Yep, it's got a room for you to continue to add, onto that router or whatever, you know. The third topology here is a ring topology. As you can see, it's got a shape of a ring. Characteristics are, it is a complete ring formed. Computers connect from one to the next or use special network devices. It almost looks like a bus topology, but the difference is it's in a ring form. Data are passed from one device to the next until they reach their destination. So if I've got two devices before me and I got information that should be routed to me, it's going to pass through those other computers before it gets to me. The amount of cable used is good midwise. So it's almost like the bus topology, right? So it's not too expensive because you don't have to, every of those devices, they don't have their own routers. It is easy to troubleshoot. Yep, it is easy to troubleshoot because if you send a data that has to go through two computers before it gets to me, if it doesn't get to me, you can either narrow it down which of the computer that the data stops at. So it's easy to troubleshoot. Faults in the ring can affect the entire network. Yep, that's right. If you've got to have to fix the problem, right, you're going to have to disrupt the other computers that are on that network. The fourth, the mesh topology. Characteristics are very straightforward here. Requires that every device on the network be connected to every other device. So mesh, right? They interconnect. It is more difficult to implement, yeah. Uses a high amount of cabling. Yep, high amount of cabling is involved. And has many connections on each device. Has the highest level of redundancy, which therefore means when you send the data to a machine, there's going to be too much of looping. That's why it's got a highest level of redundancy. And upgrades and changes can be made with no effect on the rest of the network. Yeah, because it's intertwined, and if there's a failure, right, from just look at a road network that has secondary roads. If the main road is blocked, you still have other avenues, to get in or get out. So it's the easiest to troubleshoot. Yeah, because it's got all the cable, and if one cable fails or one connection fails, you can easily tell. You can narrow that down too. So the easiest it's become to troubleshoot. It's how expensive it is because it's got too much cabling in it. The fifth type is the ad hoc wireless topology. Looking at the diagram here on figure 2.13, realize that the physical layout is not inhibited by the use of wires. So you could tell it's a wireless connection. Networks like this are created when two or more devices with radio frequency transceivers come within range of one another and support ad hoc networking. There is no cost in cabling. The only cost is wireless adapter, network interface card, or the network interface card. Troubleshooting and maintaining connections can be difficult, and not all ad hoc protocols are the same. Multi-point wireless topology, that's the next. Its characteristics are they can have many devices attached and each communicate with a wireless bridge. So it's almost like this, but it's just got many devices. Multi-point wireless. So you've got a wireless access point. So this is, the ad hoc is kind of like two devices. But in this case, we have a wireless access point. A wireless bridge is also called wireless access point, like I said. There is no cost for wires. but there is a cost for the wireless access point device. Yep, you're gonna have to pay for this. For instance, you have like the MiFi. Troubleshooting is easier than for ad hoc wireless. All devices must conform to the standard of the wireless access point. Yep, whatever if they're required to access it using a password, yep, they gotta have to meet up with that standard. And to also understand the network architecture, it's important to know the various network types. Let's begin with the local area network. It's self-explanatory. Within a limited geographic area, like an office, home, floor, or a larger building. So, wide area network. It connects multiple offices or buildings together over a large area. The Internet Area Network breaks the mold of typical local area network and wide area network definition. This term has been around for a very long time. This includes extension of cloud-based services. For instance, you could have a local area network within an office or home, but you're receiving cloud-based services. For instance, you having your applications hosted elsewhere. Somebody's server instance, like in AWS, you can name the rest. That's an example of an internet area network. Border network components. These various network types operate with the assistance of border network components. When we talk about border network components, we're talking about firewalls and proxy servers. They are hardware that often used between different networks. It's like you have an office building, and you have an office building, and then you have somebody that, like a security guard. That's what the firewall is all about. And here it says the purpose vary, but all generally enabling varying degrees of security at the internet work connections. And these are some of the functions. You've got a packet filtering firewall. So the various firewalls are described based on what role they do. You got a packet filtering firewall. Packet filtering firewalls operate inline at junction points where devices such as routers and switches do their work. That's very important for you to understand what this device does and where it's positioned. So it's positioned at the inline. It operates inline at the junction point where devices such as routers and switches do their work. Keep that in mind. They do not route packets, but they do compare each packet received to a set of established criteria, such as the allowed IP addresses, packet type, port numbers, and other aspects of the packet protocol headers. So their role is not routing, but their role is just to kind of like, hey, when the packet comes in, check it out. If he has the right IP address, let it go. If he doesn't, block it. That's what they do. So packets that are flagged as troublesome are, generally speaking, unceremoniously dropped. Like I said, blocked, dropped. Of course, they are not being forwarded. Circuit level gateway. Quick way to identify malicious content. Circuit level gateways monitor TCP handshakes and other network protocol session initiation messages. So if you read and understand what TCP handshake is, when your computer initiates a request, it does a handshake and say, hey, I'm looking for this. It says, yeah. So that's basically what they do. So they go into that and they monitor that, and the TCP handshakes and other network protocol sessions initiation messages. The initiation messages across the network as they are established. Next, stateful inspection firewall. Unlike circuit level gateways that check handshakes, TCP handshakes, these are state-aware devices that not only examine each packet, but also keep track of whether that packet is part of an established TCP or other network session. They do offer more security than either packet filtering or circuit monitoring. The application level gateway. It is an application level. It is technically a proxy, and it's sometimes referred to as a proxy firewall. It does combine some attributes of packet filtering firewalls that we mentioned with those of circuit level gateway. The destination port specifies the service for which the packets are intended. The application level gateway filters packets not only according to the service for which they are intended, but also by setting other characteristics, such as the HTTP request string. Although the gateways that filter at the application layer provide considerable data security, they can dramatically affect network performance. Keep this in mind. The next generation firewall, NGFW. So a typical next generation firewall combines packet inspection with stateful inspection. So it's got both. Therefore, it includes some variety of deep packet inspection and other network security systems such as intrusion detection, prevention, malware filtering, and antivirus. Keep those in mind about the next generation firewall. It's robust. Another network type is the visual networks. There are two. We have the visual private network and the visual local area network. VLANs provide a way to separate a switch into individual broadcast domains. So you want to keep this in mind about VLANs. The diagram on figure 2.15 shows how the VLANs is configured on switches for individual broadcast domains. So if you look, 3 of the floors house have 3 different research departments, let's see, that do separate work and have separate network resources. In the past, each of the departments would have been located on a separate floor, and the resources that they needed to access would be located on the department's network segment. But with the help of VLANs, right, you're able to break that in. So with all this setup, where all 3 departments are connected on one router and separate network, with the help of VLANs, like I said, it can be configured on switches. That's done the other way. Connected into the same switch. Their ports can be configured to the different VLANs which represent their individual subnets. This setup allows them to access the resources on their subnet. Another network type is the visual networks. 2 types of visual networks are the visual private network and the visual local area network. Visual local area networks can also be configured on switches in today's world. They do provide a way to separate a switch into individual broadcast domains. The diagram on figure 2.15 shows a VLANs that is configured on switches for individual broadcast domains for a research department that's located on 3 different floors. The diagram on figure 2.16 shows that department how it's able to be assigned to different VLANs connected to the same switch. VLAN 1, VLAN 2, VLAN 3. Considering that network architecture has to do with an arrangement of links, it's important for us to know about link types. Each port can be configured into one of 2 types of links, either as an access port or a trunk port, but not both. Access ports can generally belong to only one VLAN. Traffic is both received and sent unchanged as it was sent from the end station or host. Trunk ports. The name trunk port came from the telephone companies. Trunk ports on network switches can carry multiple VLANs at the same time. Assume that you've read this, read it for your understanding, trunk protocols, and also we've also got that visual private network. It is used frequently. It has different meanings, of course, the term, depending on the context. A visual private network is a method for connecting 2 disparate networks, generally over the internet. The key takeaway here is IPsec is the standard used in this. And what is IPsec? IP security, and is based on a series of requests of comments that were first issued during the mid to late 1990s. Some of the standards are authentic header, encapsulated security protocol, internet key exchange, internet securitization and key management, secure hash algorithm, the SHA-1, MD5, 3days, AS. You can read the details for a better understanding of this course. You can go through and kind of read all those standards. Read about generic routing encapsulation. Software-defined networking. The implementation of software-defined networking has varied depending on the vendor and the technology being used, and a common definition is elusive. Today, software-defined networking is being used in many areas, including wide area network technologies, storage, data center, wireless, and even down to the access layer on switches. It is largely based on separation of logical hierarchy of network devices. The lower level is typically called the data plane or the forwarding plane. And the plane is where the device, the network device, does the actual work, forwarding frames and packets. The next level is the control plane, where the logic, configuration, and management of the device occurs. The table on figure 2.17 shows us the pros and cons of the SDN. centralized provisioning, scalable, provide security, reduce hardware print. However, that comes with some latency, that centralized provisioning. Scalability impacted by device management limitation. Security, yeah, it increased complexity of network management. You can just rate these two types of two. You can go further. You can read a little bit detailed on software-defined wide area networks and software-defined access, just to get a better understanding of how they do operate. The diagram in figure 2.18 shows you a standalone solution versus a controller-based solution. We've come to the conclusion of our chapter 2. You can do some knowledge check just to get a better understanding. One of the things that stands out here in chapter 2 that you have to focus is to get a better understanding on how VLANs do operate and how they're configured on switches to be able to have multi-users be able to leverage the capability that VLAN do offer.